Okay, so we want to solve the Laplace equation. Like I said, the minus sign there is there for psychological reasons, mainly, I mean, good mathematical reasons as well, but ultimately just psychological reasons. What we want to do is we want to solve this equation, and remember this equation here is the same as the double x derivative of u plus the double y derivative of u is equal to 0. X and y here are both space variables. It is wrong to think about either one of them as a time variable. They're both space variables. Wrong in the sense that it leads you to bad intuition. So this equation here is equivalent to this equation, and these are just different ways of writing the same thing. Now, when we talk about solving Laplace's equation, we have to talk about the domain in which we're going to solve it. Because if you think about just, the Laplacian of u is equal to 0, well, there's a lot of different functions that satisfy that. So we're going to solve this first on the upper half plane, that is on the set xy, where y is bigger than 0. And then we're going to give it boundary values. We're going to say u of x u of x comma 0 is equal to some prescribed boundary data f of x. And just to sort of give you the schematic of what this looks like, this is x, this is y, so we're working in the upper half plane. For a number of reasons, this is a very important space to work in mathematics. Okay, so what we're going to do to solve this equation is we're going to take the Fourier transform of the equation in the x variable, and we're going to treat y as constant. Now I'm going to tell you, this is the second or third time I've had to make this video, because when I start doing these computations, sometimes I write y instead of t, and the other videos I was doing that too many times so that it got too confusing. Hopefully I do that. My goal is to do that 0 times in this video, but I want you to be warned, if you ever see me writing a t, I will fix it eventually, but I mean for it to be a y. It's just because I'm thinking, I just made the diffusion equation videos. But this is called a time-dependent or time-independent equation. It doesn't depend on time. So if you see me writing a time, it's just my lack of attention to detail, and I should be writing a t instead of a y. Or I mean, I should be writing a y instead of a t. At any rate, we're taking the Fourier transform in the x variable, and similar to what we did when we had the diffusion equation, the double, when I take the Fourier transform of that, it's just going to be the double y derivative of the Fourier transform. So if I take the Fourier transform of this equation, I'm doing it in the x variable, so the Fourier transform of the double x derivative is minus omega squared times u hat of omega y, plus the double y derivative, well, this is just the double y derivative of omega y, or the double y derivative of the Fourier transform. Okay, for similar reasons as it was with the t variable, and then the Fourier transform of 0 is 0. Okay, so now we can rewrite this, and we get the double y derivative of omega y is equal to omega squared times u hat of omega y. Now remember, the variable in which we are doing the differentiation is the y variable, not the omega variable. So as far as y is concerned, omega is a constant. So this is a second order differential equation. I will pause for a moment while you think about what the solution to this equation is. Okay, hopefully you paused and you remember that the general solution is u hat of omega y is equal to a times e to the omega y plus b times e to the minus omega y. Now, this is a different differential equation for every omega. So just like with the diffusion equation, these unknown coefficients depend on omega. So I'm going to put that there. Okay. So what we want now, a of omega and b of omega, these are arbitrary constants. At least they're arbitrary in some sense. They do need to be consistent with our boundary data here. Okay, so what we want to have happen though is we want to be taking the inverse Fourier transform of this. So when we take the inverse Fourier transform, if you look right here, when omega is positive, we're going to get some, so notice that y is always positive because we're in the upper half plane. So here, when omega is positive, okay, when omega is positive, this is going to be bad because we got some exponential blow up here. So what we're going to do is we're going to say a of omega is equal to 0 for omega greater than 0. Okay, now over here, what do we have? Well, we have sort of the opposite problem. We're good when omega is positive because minus omega y will be positive and we get good exponential decay. So we're going to say b of omega is equal to 0 for omega less than 0. Okay, so this is another weird part here. Actually, we'll just say less than or equal to 0. Okay, so this is a weird thing, one of the weird things that we're doing when solving this differential equation using Fourier transforms. And I'm saying this is one of the weird things, like I've referenced there being weird things before, but that might have been in one of the earlier videos that I made here. So what I'm saying, what I started the other videos off by saying is that we're going to use a Fourier transform to solve this differential equation, but there's going to be some weird things that we do. But we will actually we're going to get a formula, and then there's going to be some very long and tedious estimates that we will prove to prove that what we actually have is a solution to the differential equation. Okay, so at any rate, what we have then is u hat of omega y. We're going to have two different things. When omega is less than 0, it's going to be b of omega times e to the minus omega y. This is omega less than 0. And then for omega less than or equal to 0, and then we have a of omega times e to the omega y, where omega is greater than 0. Okay, so I'm about to make some changes here because I don't want to keep rewriting everything. But notice that if omega is positive, the absolute value of omega, I got this backwards. I got that backwards, sorry. When omega is a of omega is equal to 0 when omega is greater than 0. So we've got a of omega e to the omega y, and this is going to be for omega less than 0. So omega, a of omega is equal to 0 when omega is greater than 0, so it's not equal to 0 when it's less than or equal to 0. Sorry about that. And then when omega is greater than 0, we're going to have the b of omega. So this is b of omega e to the minus omega y, and this is going to be when omega is greater than 0. Okay, now let's look up here. Omega is a negative number. So if it's a negative number, I can write minus the absolute value of omega. Like if omega is minus 5 is equal to minus times the absolute value of minus 5. Again, similarly up here, omega is a positive number, so it's equal to its absolute value. So we can write it like this. Okay, but then notice what we can do then. Both of these have the same factor of the e to the minus absolute value of omega I. So I can write this as u hat of omega y is equal to e. Let me do this in blue so you can just sort of track that I'm making a change here. This is e to the minus absolute value omega y. And I'll get rid of it here and here. Okay, but now, a and b are just arbitrary functions, so I'm just saying it's one arbitrary function when omega is less than or equal to 0. It's another arbitrary function when it's greater than 0. These are, they're not non-zero at the same time. So instead of writing it like this, I could just write it in this way. Just combine those into one function and write it as big F of omega. where this is sort of, at this point, an arbitrary function. Okay, but now we can use our boundary data here. And notice that u hat, when y is equal to 0, we've got u hat of omega 0 is equal to 1 times f of omega. Okay, but that's just the Fourier transform of this, which is f hat of omega. So this is f hat of omega. Okay, so in other words, this big F of omega is really just equal to f hat of omega. I use that notation because it's suggestive, because big F is also used to mean the Fourier transform of little f. Okay, so what we have then is a Fourier transform. What we have is a Fourier transform of our solution is e to the minus absolute value of y times f hat of omega. So I'm basically going to erase all of this and just put that up there, and then we're going to start working with that. All right. So then what we have is we know that u hat of omega y is equal to f hat of omega times e to the minus absolute value of omega y. Okay, so I made a mistake, and then I had to redo the last several minutes of video. So I think I'm bouncing back to where I was. So I want to find the inverse Fourier transform of this whole thing. I know the inverse Fourier transform will be the convolution of the inverse Fourier transform of these two. So I need to figure out what the inverse Fourier transform of this is. Well, you might remember that we computed something like this. We might have actually computed the Fourier transform, but from that I'll let you figure out the inverse Fourier transform. This is equal to the square root of 2 over pi times a over x squared plus a squared. We're going to do this when a is equal to y, so we have something like this. Okay, so then u of xy, we're going to be doing the convolution, or really technically 1 over the square root of 2 pi times the convolution, and then we're going to look at the integral. Now, in the beginning of the video, I said wherever you see a t variable, there's a mistake. The variable of integration in the convolution integral is now going to be t. If you think back to the diffusion equation, t and x were our variables, and y was a dummy variable in convolution. Here, x and y are our variables, so t will be the dummy variable in the convolution. And this is a very standard thing to do. It's not just a me thing. So we look at the t going from minus infinity to positive infinity, and now over in this function, wherever I see an x, I'm going to put an x minus t. Because remember, we're doing the Fourier transform, and therefore the convolution in the x variable. So this is going to be the square root of 2 over pi times y over x minus t squared plus y squared dt. I'm going to move this on the outside of the integral, this square root of 2 over pi on the outside of the integral. Those square roots cancel, or the square root of 2's cancel, and then we end up with 1 over pi times the integral t equals minus infinity to positive infinity f of t times y over x minus t squared plus y squared dt. Okay, and now my claim, I'm not going to prove it in this video, but my claim is that that is a solution to this problem over there. It's Laplacian, it's 0 in the upper half plane, and its boundary values, that is, when you think about y being equal to 0, or take the limit as y goes to 0, you're going to get f of x. Those are not, those things, well, they'll take a little, there's some technical math that we have to do to kind of prove it. Now, maybe you're wondering, like, why do we have to do that? Because we kind of started with this, and this is the formula that we got after doing this valid method. But remember, there were some weird things that we did in there. And we're actually going to prove this when we take Fourier transforms of things. We sort of have to assume that f is going to be, in L1, or that it's integrable, absolutely integrable. But we're actually going to prove that this gives us a solution to the Laplace equation whenever f is like continuous and bounded. This will give us a solution. So for example, like just a constant function 1, this will give us a solution to this problem here. Okay, that's it. I'll do that in the next video, or probably it's going to be actually the next several videos.